When we started this conversation, you said you went into graduate school because you wanted to understand the quantization of maybe space-time itself. Like, how far does this quantization principle go? It doesn't sound like
Yeah,
anything here implies space-time is not continuous. It doesn't sound like space-time's discrete. It still sounds like
yeah,
you're assuming a continuum.
yes, you're right. Um, Initially, when I first confronted the finiteness of black hole entropy, why isn't it infinite given that there seems to be an infinite entanglement? I thought perhaps the answer was that there's some discreteness and there's some shortest cutoff. But I just gave you a different way of trying to answer that, which was that no, it's because at very short scales, the gravitational interaction is so strong that space-time is very curved, and I can't even dis- distinguish which side of my imaginary boundary my degrees of freedom are living on. And that doesn't require discreteness, it looks like. So I think, yeah, this line of thinking led me away from the idea of discrete space and time, at least for the moment. I think in the long run, it will lead back to that. But this relates to some other questions that you teed up to ask me, which is about like, um, what is the relation between emergent gravity and space-time and the problem of quantum gravity?
Right.
Like, where are we on the path? What is the role that thermodynamic reasoning and accounting of the Einstein equation as an equation of state could play in leading us to better understanding of quantum gravity? And I do have an answer I'll give you for that. I think of it as analogous to the role that thermodynamics played in the history of physics so far. So think about when Carnot initially was trying to account for a theory of the efficiency of heat engines, right? He had the concept of caloric, which turned out to be an incorrect version of the concept of heat, right?
Uh-huh.
But it was sort of right, and he actually got a correct thing. That's why we call it a Carnot cycle. He inferred that there's a maximum possible efficiency of a heat engine, um, which is attained by a reversible heat engine. But then other physicists came along after him, like Clausius and Kelvin, and refined it and said, no, actually, that was a good idea, but actually, there's no such thing as caloric. Caloric is really just a form of microscopic energy of the degrees of freedom, like kinetic energy and potential energy. And moreover, unlike what Carnot thought, caloric is not conserved because it's heat, and heat is not conserved. Heat can do work, for example, and you can lose the heat and turn it into work partly. So, or you can create heat when you didn't have it to begin with, like by friction or something. So, but nevertheless, the process of figuring out, well, why was Carnot getting something right, but not everything right, led physicists to a better understanding of what is the nature of heat. And that led into also what is the nature of statistical mechanics? Like how do we account for the gases in a heat engine from a microscopic viewpoint using statistical mechanics? So, and another example is with quantum mechanics. Late in the 19th century, Max Planck is trying to understand how can we apply this thermodynamics, which seems to work great for gases, to electromagnetic radiation? What if I have an oven in thermal equilibrium full of radiation?
Uh-huh.
Let me try to count its entropy and account for the distribution of energy among its frequencies or wavelengths. And that was actually impossible to do with the physics that he had at the time. But he found a formula that worked perfectly, the Planck distribution. Then he tried to account for, okay, I better find a theoretical explanation. Why is this the right formula? And he tried to do it with the physics he had, and he couldn't, because physics needed a new idea, which is quantum mechanics, in order for that to make any sense. So the effort, see, here's the deal. Thermodynamics is I call it fault-tolerant theory. It can get some things right without actually having the correct foundational microscopic picture. And in fact, you can even have fundamental mistakes, like Carnot had the mistake. He thought that caloric was fundamental and that it was conserved, and it wasn't. But he still got the right answer
Hmm.
for the maximum efficiency of a heat engine.
Interesting.
And that it's a universal maximal efficiency determined by the temperature of operation and the temperature of the reservoir that the heat flows to. That's amazing. So similarly, I think of what I'm doing in that kind of a way. I'm using robust thermodynamic concepts that are probably going to be correct no matter what the right microscopic picture of space-time and quantum gravity is. And some of what I'm trying to do is probably nonsense, the way Carnot, some of what he was doing was nonsense. But it's pushing us into the right place, asking the right questions, confronting us against the right problems that hopefully can lead to a refined understanding. Now, whether that refined understanding will require space and time to be discrete, ultimately, I don't know. I suspect it will, but that's pretty much purely a bias based on almost philosophy. If you ask what is non-discrete space-time, what is the continuum? What is a real number? Right? You say that I was treating space, general relativity and all of physics today uses real numbers to coordinatize space and time. What is a real number? If you think about it, it's a very idealized extrapolation of a notion of counting. And I think it's most likely that it's not an idealization upon which the world is built. Do you see what I mean? At its fundamental level. It's just a convenient idealization so far in physics. But that's a side question of whether we'll ever get there to a discrete understanding.
Well, what sort of discretization of space-time do you imagine? Because it can't be, well, I don't imagine it could be a naive one where you just discretize space, because then you would break some of the other symmetries that are important.
Exactly. Absolutely. And you also can't, for similar reasons, you can't discretize time just naively. Can't be like a lattice. Moreover, it actually has to be non-local in some sense. I actually thought about this in relation to another question that you sent me, which is if space-time emerges, what does it emerge from?
Right.
So this is related to the question we're talking about. So there's a very interesting observation by Don Marolf of UCSB about a constraint on possible emergence of gravity. He made a pretty cogent argument that gravity cannot emerge, gravity, I would say in space-time also, from a system which has locally defined observables that can be simultaneously precise at space-like separation. So technically what he's saying is it can't be described by commuting operators. Sometimes people try to make up an analogy between space-time and condensed matter systems. And there's even papers about emergent gravity in condensed matter systems.
Uh-huh.
And it is possible to actually have emergent spin-2 effective field theories, but they are not gravitational. Marolf made the observation that if something really behaves like general relativity, emerges that way, the Hamiltonian that governs its time translation has to be a flux integral at the boundary, let's say a large spatial boundary. And then he inferred from that no system with that property can emerge if its starting point is based on local kinematics with observables that commute with each other at space-like separation. This is a bunch of technical words, but the concept of it is that there must be a non-locality built into the very structure from which space-time and gravity are emerging. So, like you said, it can't be something naive or simple-minded. It's not just discretizing. I don't know what it is, frankly. I think it's sort of beyond my conceptual horizon at this point to be able to do it. Although I must admit, I play around with ideas sometimes on the side.
Yes.
Like sort of what would be the simplest discrete thing I could build a universe out of? And I try things out.
On the side, but not published.
No, although I'm thinking of publishing something soon on an idea. But I don't see a direct connection between that idea and the physics we know well. So it's really kind of a flaky idea in that respect.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist.